Europe called America's mills wasteful. Then their forests collapsed under drought, pests, and mismanagement. And the irony was inescapable. The US had quietly built a circular machine. Lasers, 3D scanners, curve saws, and a byproduct economy that turns bark into mulch and sawdust into export-grade heat. You're about to watch a single log move through a mill that acts more like a Silicon Valley factory than a lumber yard, where nearly 100% of that tree is used, and waste becomes revenue. The question is simple. How did an industry once throwing away 70% end up with almost nothing left in the bin? The answer was not bigger blades. It was a different brain inside the building, turning a single tree into a set of decisions. A log that once shed most of its mass now exits with almost nothing left for the bin because the mill treats wood like data, not debris. A truck backs in, stakes creak, and one log rolls onto steel. It's tagged for traceability, stripped of bark, probed for moisture, and routed. The floor looks less like a saw shop and more like a fulfillment center. Conveyors, scanners, and gates sorting flow as if each stem were a SKU with a value profile waiting to be unlocked. Old mills tried to fix crooked wood with straight lines. The forest didn't cooperate. Decades of drought stress, tight rings, taper, sweep, and knot clusters created geometry that punishes linear thinking. The problem was simple to state and hard to solve. Convert bent inputs into straight, sellable boards without bleeding fiber, grade, or time. The first real move happens before steel meets wood. Multiple laser and 3D scanning heads sweep across the log, measuring taper and ovality, locating rot pockets and knot clusters, reading sweep down the length. In milliseconds, the software runs thousands of cut plans, each a hypothesis about where value hides. How many studs, which faces produce appearance grade, where defects must fall so they get trimmed out downstream instead of erasing a premium face. That simulation doesn't chase sheer volume, it chases revenue. The head rig takes instructions that privilege grade recovery over raw throughput, because a smaller count of higher-grade boards often beats a larger stack of low-margin pieces. The system assigns a cutting pattern, face openings, rotation, and depth, so the first cuts set up every downstream station to win. Then the machine does something counterintuitive. It stops fighting the tree's arc. The curve saw tracks the natural sweep of the log, guiding blades along a shallow path that keeps fibers continuous instead of shredding them into waste. That single pivot lifts yield by 5 to 10%. Scaled across a plant that runs day and night, the added board feet are measured in the millions, and the profit per log changes with them. The choreography that follows is fast, precise, and unforgiving. Sideboards peel off and ride their own lines. The heart of the log becomes a cant and shoots forward, where resaws split it into targeted dimensions. Edgers square and resize the sideboards to spec, shaving defects, tightening tolerance. Trimmers cut to length while pushing knots and streaks out of the critical zones that determine grade. Every machine is a move in a larger game. Position defects where they cost the least. Reveal clear faces where buyers pay the most. Keep fiber intact so weight turns into dollars instead of dust. Inline grading no longer leans on a glance and a pencil mark. Cameras and machine vision inspect faces at speed, flagging wane, slope of grain, knot frequency, and color variation with consistency that doesn't fade at the end of a shift. The result is stable, repeatable classification that keeps the mill aligned with market tiers and contract specs. When the price for a certain stud rises, the cut plans adjust. When appearance grade demand softens, the algorithm shifts volume toward dimensions that move. This was not a saw blade story. It was a control system story. By the time the boards clear the trimmers, the log has become a portfolio. Studs that meet tight structural grades, appearance boards with clean faces, dimension lumber-sized for framing packages. The yield profile is engineered by software, but paid out by steel and motion. Material that once fell as useless offcut now exits as product with an address in the order book. The lesson was harsh but clear. Treat the tree as a chaotic shape and you waste it. Treat it as a mapped asset and you extract almost everything that counts. But the real leverage lies below the deck, where nothing is allowed to fall far. The belts and blowers waiting under the line turn the leftovers into their own set of products and their own cash flow. How does sawdust turn into money that can rival the boards themselves? The answer lives in the space under the main line, where every stray fiber is captured, counted, and redeployed. This is the hidden factory. Belts run under chutes, blowers pull fines into ductwork, cyclones spin out dust, and silos meter flows to whatever process needs feedstock next. Nothing drops to the floor. Everything finds a path. The old model treated residues as a nuisance. Burn piles, open pits, and trucking fees turned leftovers into a cost center. That vanished when energy prices rose, emissions rules tightened, and downstream buyers began paying for consistent streams of bark, chips, and fines. Incentives flipped. Waste became inventory. The system shifted from disposal management to product scheduling. Start with bark. Screens separate fines from long flakes, magnets pull tramp metal, and colorants coat ground bark to meet regional landscaping palettes. The market is local and heavy. Haul distance eats margin fast, so dispatch focuses on radius and backhauls. Mulch moves in seasonal waves, and mills that manage stockpiles and trucking windows keep the spread between selling price and diesel costs. The constraint isn't demand. It's logistics. Chips sit in a different tier. Classifiers grade by size and bark content. Overs go back through a rechipper, pins fall into the fine stream, and the sweet spot feeds pulp contracts and fiberboard furnish. These contracts buy volume but demand uniformity, moisture control, and predictable delivery. The mill gains cash flow stability. The buyer gets a steady diet that keeps digester chemistry and panel density within spec. The system trades flexibility for reliability, and both sides profit from the rhythm. Sawdust and planer shavings become densified fuel. Dryers pull moisture down into a tight band. Hammer mills bring particle size into range, and pellet presses compress fines into cylinders that hold together in handling but fracture cleanly in combustion. Quality turns on ash and moisture. Too much bark or grit, and you fail the premium grade. Too wet, and you lose durability, storage life, and energy density. At the gate, this is a simple product. Inside the plant, it is a narrow target hit by controls. The payoff is scale. Fuel pellets move by the truck, the train, and the ship. The United States became the world's leading exporter of wood pellets in 2024, moving more than 10 million tons, with demand anchored by domestic heating markets and buyers in the EU and the UK. That offtake is bankable. It justifies capital for dryers, presses, and loadout, and it turns a volatile residue stream into long-term revenue. Residue doesn't just leave the mill, it powers it. Hog fuel, bark, and fines feeds on-site boilers. Those boilers heat dry kilns, reducing cycle time and defects in finished lumber. In combined setups, turbines spin from steam, offsetting purchased electricity and smoothing energy costs that would otherwise swing with the grid. The loop is tight. Logs in, products out. Heat recaptured, power generated. Emissions controlled through modern filters. Energy becomes another product of the line. What looked like housekeeping is, in truth, an operating system. Metering bins, variable speed drives, and moisture sensors act like a refinery's control room, allocating flows in real time to the highest return. If mulch inventory swells, dispatch prioritizes local landscaping orders. If pellet buyers post a premium, dryers pull more fines from the stream. If pulp contracts tighten specs, chip classifiers shift cut points to bias cleaner furnish. The plant arbitrages in fiber form. The reuse rate clears 95% in mills built for this model. That is not a slogan. It is cash flow architecture. Bark supports landscaping revenue, chips monetize the middle, pellets convert fines into export-grade fuel, and the boiler cuts the power bill while stabilizing kiln schedules. Some operations cover a significant share of their energy needs internally. That reduces exposure to price spikes, keeps uptime high, and protects margins when lumber markets weaken. The lesson was harsh but clear. Waste disappeared because it became a business unit. The hidden factory didn't just lower disposal costs. It created products, contracts, and power. This closed loop redefines wasteful. But the comparison only lands when set against the European paradox, where capacity and timing, not ideals, decided what burned and what paid. Europe mocked the American mill as crude, too fast, too hungry, too industrial. Then the forest dried, beetles multiplied, and slash stacked up. The paradox sharpened. The US model that looked wasteful from afar turned circular in practice, and it moved when time mattered. A decade of essays and panels cast US mechanization as blunt force. High-feed saw lines, massive yards, contract trucking, and non-stop shifts. The European preference leaned smaller. Selective cuts, shorter days, tighter rules, and slower throughput. The argument sounded moral. The difference was mechanical capacity. Heat and drought stressed stands across Central Europe. Bark beetles found open lanes. Dead and dying timber rose in volume until the roads, the crews, and the mills fell behind. Where cut and haul lagged, trees stood, dried, cracked, and lost value. This was not a single-season spike. It was a stacked problem. Water stress, pest load, and fuel accumulation, each compounding the next. Mill constraints set the clock. When regional capacity is thin, salvage windows close early. Fiber dries, checks, and stains. Pith splits crawl down the length. Blue stain creeps into sapwood. Board grades collapse while the market floods with distressed logs that no line can clear. Fires don't negotiate with spec sheets. They erase habitat, storage piles, and the next decade of revenue in one pass. Meanwhile, US regions with mature mill networks, dense clusters in the South and the Pacific Northwest, ship staggering volumes year after year. That rhythm matters in a crisis. When wind throw or beetle kill hits, salvage moves. Logs meet scanners, curve saws preserve fiber, residues drop into energy lines. Carbon locks into products. Fines move as pellets. The machine turns decay into output rather than letting value evaporate on the stump. Policy added a second layer. In the US, emergency declarations cleared paths for fuel thinning and accelerated salvage. Critics warned about overreach and ecological risk, but the capacity existed. Iron, crews, and buyers ready to take material when the windows opened. The lesson was harsh, but clear. Action without machinery is a press release. Action with machinery is a supply chain. Logistics wrote the balance sheet. Without nearby mills, haul distance kills value. Every extra mile adds diesel, driver time, and tire wear, while the log dries and the grade decays. Europe's patchwork capacity, combined with permitting friction and contested policy, slowed response in key regions. Loads waited. Prices slipped. By the time trucks found a buyer, the fiber was worth less, and more of it moved straight to low-grade outlets or burn piles. Environmental stakes rose with each delay. Dead fuel stacked deep. Fire intensity climbed. Pest fronts expanded into stressed adjacent stands. In an active network, mills pull risk out of the forest continuously. Small removals, steady thinning, routine road use. That cadence spreads disturbance across time and space, keeping heat out of the canopy and cash in the system. The contrast was not philosophical. It was operational. Think about two reservoirs separated by a gate. One sits behind a wide spillway that releases steady flow before the pressure cracks the wall. The other holds back water behind a narrow slot that clogs with debris. The first looks aggressive. The second feels careful. Only one avoids failure under stress. Forests behave the same way when the inputs are fire, beetles, and drought. Residue handling closed the loop. In the US system, more than 95% of mill material finds a use. Mulch, chips, pellets, heat, power. That monetization keeps mills running even when lumber prices fall, which keeps the salvage valve open when disturbances surge. The cash cycle funds resilience. The system pays for its own readiness. The irony was inescapable. Scale, once framed as waste, functioned as a resilience engine. Fast salvage, high utilization, low waste. Thin capacity, however principled, left value uncut, fuel unthinned, and risk compounding. If this map of the hidden factory changed how you see a 2x4, say so below, and subscribe for the deep dive on pellet economics and salvage timing. We'll trace price bands, kiln energy offsets, and salvage windows as markets tighten. When forests heat up and windows close fast, which system would you trust?